Welcome to the API 571 Audio Masterclass series. This episode is brought to you by Mag Integrity. For the complete high-resolution study guides, API 571 exam prep question banks, and to unlock our full private audio library, visit our premium engineering portal at magintegrity.ca. So imagine you're injecting a chemical, right, into your multi-million-dollar refinery piping system, and you're doing this specifically to save it from acid corrosion. But you find out you've just triggered a microscopic, basically catastrophic unzipping of the metal from the inside out.
It's a terrifying scenario.
Right, like you solved one problem, but you inadvertently set this ticking time bomb right in the atomic structure of your equipment.
You did. And that's exactly the fundamental paradox we're exploring in this deep dive today.
Exactly. So today we are unpacking a highly specific, critically important damage mechanism documented in API-RP 571, Section 3.4. It's known as Ammonia Stress Corrosion Cracking, or Ammonia SCC.
Yeah, and for those of you dealing with the integrity of fixed equipment in, refining or petrochemical environments, this is really one of those mechanisms that requires a flawless understanding of metallurgy, chemistry, and mechanical stress all at once.
It's just a huge topic. So our mission today for you, the listener, is maximum knowledge density without the fluff. We're going to go from the microscopic metallurgical theory, right up to the macroscopic refinery impacts and actual field inspections.
Which is necessary because you have to look at the equipment not just as static pipes and tanks, but as, dynamic chemical reactors.
Right, because people tend to think of corrosion as just rust, right?
Exactly, like a slow, predictable, uniform thinning of a metal wall. And you can measure rust. You can just watch it over years.
But environmentally assisted cracking and ammonia SCC specifically, that completely defies that logic, doesn't it?
It absolutely does. The component might look entirely intact to the naked eye. The wall thickness could be, 100% original.
But there's a problem hiding inside.
Right. Initiating from just a microscopic surface flaw, a crack network is aggressively driving its way through the wall thickness.
And this doesn't just happen out of nowhere. You need a very specific triad to initiate this failure, right?
Yeah, you need three things perfectly aligned. A susceptible material, a high tensile stress, whether that's applied or residual, and an aggressive chemical environment.
Okay, so let's start with that first one, the materials. Specifically, I want to get into the atomic architecture of how these cracks actually propagate because, it isn't the same for every metal.
No, it's not. We really have two primary categories of susceptible materials to look at here. You've got your copper-zinc alloys like brass and specific Admiralty brasses, and then you have your basic carbon steels.
And the cracking morphology, meaning, the actual physical shape and path of the crack, that's radically different between the two, right?
Night and day difference. The physical evidence left behind is completely distinct.
Okay, break that down for me.
Sure. So when you look at copper alloys under a microscope, ammonia SCC can manifest as either transgranular cracking or intergranular cracking.
Okay.
And which one you get, that depends heavily on the specific chemical soup the alloy is exposed to and the magnitude of the stress.
Hold on, let me try to visualize this, because we always talk about grains in metal. If we imagine the metal not as a solid sheet, but like a brick wall.
I like that analogy, yeah.
So transgranular cracking would be like taking a sledgehammer and smashing straight through the bricks themselves, right?
Exactly. You're physically tearing the internal structure of the metallic grains apart.
Right, but then intergranular cracking, on the other hand, that means the crack is following the path of the mortar.
Yes, precisely. The bricks, which are the metallic grains, they stayed perfectly intact, but the mortar holding them together basically crumbles, and the wall fails along the seams.
Okay, that makes sense.
But, the brick and mortar analogy only works if you understand what the mortar actually is in a piece of metal.
Right, because it's not actual mortar.
Right. The bricks are the individual crystalline grains. The mortar is what we call the grain boundary. And a grain boundary is fundamentally a high-energy zone.
High energy. What do you mean by that?
It's the area where two separate crystalline grids, growing in different directions during the metal solidification, crash into each other.
Oh, wow. So it's basically a collision zone.
Exactly. It's a zone of atomic mismatch. And because it's so disordered, it's where impurities, trace elements, and microscopic defects tend to accumulate.
Okay, so copper alloys can fail in both ways. They can suffer the smashed bricks, the transgranular, or the crumbling mortar, the intergranular.
Mm-hmm. Getting experienced
The
both.
carbon steel behaves completely differently, doesn't it?
It does. When carbon steel is attacked by ammonia SCC, it almost exclusively fails via intergranular cracking.
So it only crumbles along the mortar.
Right.
Why is there such an absolute difference? I mean, why doesn't carbon steel ever suffer from transgranular cracking in this specific environment?
Well, it really comes down to the underlying crystallographic structure of the metals.
Okay, getting into the deep physics here.
Yeah, but it's important. Copper alloys possess a face-centered cubic, or FCC, atomic lattice.
FCC.
And this specific geometry has multiple densely packed slip planes. So under high stress and aggressive chemical attack, the atomic bonds along those slip planes can be physically sheared.
Ah, so the crack has like a built-in geometrical pathway to just cleave straight through the crystal.
Exactly. But carbon steel is entirely different. Standard carbon steel is predominantly composed of a body-centered cubic, or BCC, ferrite phase.
Which is what exactly?
It's an iron matrix with small amounts of carbon and trace elements like manganese, chromium, and nickel.
So the body-centered cubic bricks of carbon steel, they're just fundamentally tougher to chop through.
They don't offer those same easy slip planes to the chemical attack, no. The BCC structure of the ferrite grains strongly resist being cleaved in half by the specific chemical kinetics of ammonia.
Okay, but remember what you said about the grain boundaries of a mortar.
Right. Because the carbon steel grains themselves are so resistant to the environment, the chemical attack concentrates entirely on those disordered, high-energy grain boundaries.
Wow. So it literally targets the weak points.
It seeks the path of least resistance. It dissolves or dramatically weakens the atomic bonds right at that zone of mismatch. The steel literally unzips along its microscopic seams.
And the physical evidence of this, from what I've seen in the API 571 source data, it's striking.
That was very clear when you look at it.
Yeah, like we have access to the exact microscopic analysis. If you take a cross-section of a failed copper alloy tube, right, and put it under a microscope at a high magnification, like 500x, you see this jagged, harsh lightning bolt cutting straight through the material, severe transgranular cracking.
Yeah, it's very aggressive looking.
But then you contrast that with a micrograph of a failed carbon steel component or even some brass exchanger tubes, and you see a spider web.
Exactly. It's this branched, creeping network of cracks that perfectly outlines the individual grains as they pull apart from each other.
It's kind of crazy to think about.
Well, a failure analyst relies heavily on those specific morphologies. I mean, when you slice open a failed pipe, polish it, etch it, and look through the lens, seeing that intergranular spider web in a carbon steel weldment immediately points you toward an environmentally assisted cracking mechanism.
And if ammonia is in the process stream, you basically have your primary suspect.
Exactly.
Okay, so let's transition from the microscope to the actual macroscopic components we're putting into the field. You mentioned brass exchanger tubes.
I did.
We need to define the susceptible materials strictly here because clearly not every piece of metal cares about ammonia.
No, definitely not. As we said, the primary vulnerable families are copper-zinc alloys and basic carbon steels.
And within the copper-zinc family, the text explicitly points out that the most notorious victims are heat exchanger tubes made of brass.
Yes, and particularly specific grades of Admiralty brasses.
Right. And I want to look at a highly specific case study that's documented here because it perfectly illustrates this.
Well, let's hear it.
So we have documentation of a catastrophic failure involving a very precise component. It was an inhibited Admiralty tube, UNS C44300 grade.
A very common material, yeah.
And it measured exactly 0.75 inches in diameter, Birmingham wire gauge 16.
Which means it has a wall thickness of exactly 0.0463 inches. Very thin.
Right. And crucially, it featured extruded fins. Let's dissect this. Why is this specific 0.75-inch tube, this UNS C44300 grade, the poster child for Ammonia SCC?
Well, Admiralty brass, like that UNS C44300, it's ubiquitous in heat exchangers for a really good reason. I mean, it offers excellent thermal conductivity and generally performs very well against corrosion from typical cooling water.
Right. It does its job well normally.
Exactly. But its vulnerability to ammonia is its Achilles heel. When you introduce a tube with those specific dimensions and features to an ammonia environment, you're creating a perfect storm.
I really want to focus on the extruded fins part because, you know, we use fin tubes to increase the surface area for heat transfer.
That's the goal, yeah.
But you don't just glue fins onto a metal tube. You manufacture them by essentially violently crushing and shaping the base metal.
And that is the critical mechanical factor right there. Extruding fins is a severe cold working process.
Right, because you're not melting it.
No, you are physically forcing the metal through a die at room temperature, radically deforming its crystalline structure just to pull those fins up from the base material.
Oh.
Yeah, this process fundamentally destroys the relaxed grain structure of the brass and locks an immense amount of permanent residual stress into the tube wall.
Wow. So even before you put this tube into service, before it ever sees a single drop of fluid or a single PSI of pressure, it's basically sitting there internally screaming with residual tensile stress.
Precisely. Just from the manufacturing process alone. You
Yeah.
have a highly susceptible copper-zinc alloy, and you have maximized its internal stress through cold work.
So if that tube goes into a service where ammonia is present, say on either the shell side or the tube side.
The atomic bonds in those highly stressed fins and tube walls are going to succumb rapidly to the transgranular or intergranular cracking we just detailed. The chemical environment merely pulls the trigger on the stress that manufacturing loaded into the gun.
That is a great way to put it. Now that makes perfect sense for a thin, cold-worked copper tube. But the rules for carbon steel are fundamentally different, right?
Very different, yes.
Because carbon steel isn't highly cold-worked in the same way, usually. But the API document mentions it has a hard, absolute metallurgical threshold for susceptibility.
It does. The engineering data states that for carbon steel, if the steel has a minimum specified tensile strength strictly not greater than 70 ksi, it can be immunized via stress relief.
Okay, 70 KSI. Let's talk about that.
Yeah, the 70 ksi threshold is a hard dividing line in materials engineering for this mechanism. KSA stands for kilopounds per square inch.
Right, so it's a measure of the steel's ultimate tensile strength.
Exactly how much force it takes to physically pull the metal apart until it breaks. Standard piping grades, atmospheric storage tank plates, basic vessel materials, these often fall under that 70 ksi limit.
Okay, so if you use these lower strength materials, you have an engineering out. You can apply a stress relief heat treatment to effectively neutralize the fret.
Right.
But wait, let me stop you there, because the phrasing strictly not greater than 70 ksi implies a terrifying flip side.
I know exactly where you're going with this.
Yeah, like, what if I am an engineer designing a massive high-pressure vessel, and to save wall thickness and weight, I spec a high-strength carbon steel, something rated at, say, 80 ksi or 90 ksi. Does that mean I can't immunize it? Am I just out of luck?
Unfortunately, you are operating in a significantly more dangerous regime, yes. This touches on a really fundamental inverse relationship in materials science.
Which is?
The relationship between a material's strength and its resistance to environmental cracking. When we engineer a steel to have a higher tensile strength, we generally do so at the expense of ductility.
Ductility being the material's ability to deform plastically.
Exactly, to bend, yield, and stretch without actually fracturing.
So you're saying a stronger steel is inherently more brittle?
Yes.
But how does that relate to a chemical attacking a grain boundary? Like, how does brittleness factor into a chemical attack?
Well, think about the microscopic tip of a newly formed crack. When ammonia attacks a microscopic flaw and begins to separate the grain boundaries, there is a massive concentration of stress right at the tip of that microscopic crack.
Like a wedge being driven in.
Right. Now, in a lower strength, highly ductile steel, something strictly under 70 ksi, the metal right at the crack tip can actually yield.
Oh, I see.
It microscopically deforms, which blunts the crack tip and safely redistributes the localized stress into the surrounding metal. The crack literally runs out of mechanical energy and stops.
That's fascinating. It essentially absorbs the blow by bending slightly at the microscopic level.
Yes, exactly. But a high-strength steel, something well over that 70 ksi mark, lacks that local ductility.
So it can't bend.
When the crack tip forms and the stress concentrates, the high-strength steel cannot yield. It cannot blunt the crack. Instead, the rigid atomic lattice holds all that stress perfectly in place, allowing the ammonia to continuously dissolve the highly stressed grain boundary bonds.
Wow, so the crack propagates unimpeded.
Unimpeded. This is exactly why standard stress relief treatments on high-strength steels are often insufficient to guarantee immunity against ammonia SCC. The inherent rigidity of the matrix is just too much of a liability.
Okay, so if the strength of the steel dictates the danger, then we have to talk about where carbon steel is naturally the strongest, hardest, and most brittle.
And that would be the weldment.
Right, because you don't build a refinery out of one giant solid piece of steel. You weld thousands of pieces together.
The weld is the focal point for almost all fixed equipment failures, and ammonia SCC is definitely no exception. Specifically, the real vulnerability lies in the heat-affected zone, or the HAZ.
And the HAZ, just to be clear, it isn't the melted metal of the weld itself, right? It's the base metal right next to it.
Correct. When you weld two steel plates together, the weld pool itself reaches thousands of degrees. The base metal immediately adjacent to that weld pool doesn't melt, but it is subjected to an extreme thermal cycle.
Right, because it's right next to molten metal.
Right. It heats up rapidly to near-melting temperatures, and then, because it's surrounded by a massive expanse of cold steel on the other side, it cools down violently fast.
It's basically quenched.
It is quenched, and this rapid quenching fundamentally alters the metallurgical microstructure in that narrow band next to the weld.
So it actually changes the phase of the steel.
It does. It often transforms the relatively soft ferrite and pearlite into harder, much more brittle microstructures like untempered martensite or bainite.
Oh, wow. So right next to your weld, you have accidentally created a localized band of high-strength, low-ductility steel.
Exactly. And on top of changing the microstructure, the welding process also leaves behind a massive physical force.
The residual stress.
Massive physical force. When the molten steel solidifies and cools down, it shrinks. But the surrounding cold plates restrain that shrinkage.
Because they're locked in place.
Right. The result is that the weld joint locks in severe residual tensile stress. The metal is constantly pulling against itself with this invisible force that often approaches the actual yield strength of the material.
So the heat-affected zone is just a perfect nightmare for this. You have artificially created a band of hardened, high-strength metal that lacks ductility, and you've simultaneously loaded it with extreme residual tensile stress. It is literally ground zero.
It is the exact location where that intergranular spider web will initiate the moment the chemical environment aligns.
Man. Okay, which brings us perfectly to the chemistry. We have the susceptible material, we have the residual stress, now we need the trigger. We need to look at the critical operational variables and drivers.
Right, the third part of the triad.
Obviously, the primary chemical driver here is ammonia. But the context of how the ammonia gets into the process stream, I mean, that is the real paradox of refinery engineering we talked about earlier.
It is a massive paradox.
Because in some cases, ammonia is a natural process contaminant. It's just a byproduct of breaking down organic nitrogen compounds inherent in the crude oil.
Sure, that happens.
But that's not the scenario that keeps engineers awake at night, is it?
No, not at all. The real engineering dilemma occurs when ammonia is introduced intentionally.
Okay, here we go. Explain this.
In many refinery overhead systems, you have highly acidic process streams. Hydrochloric acid, for example, might be condensing out of the vapor phase as it cools.
And acid on carbon steel is bad news.
Very bad. If you let hydrochloric acid run unchecked over carbon steel, you will suffer catastrophic uniform wall thinning in a matter of days or weeks.
It'll just eat the pipe.
Exactly. So to prevent the acid from eating the pipes, operators intentionally inject ammonia into the stream as a neutralizer.
You literally pump a basin to neutralize the acid.
Yeah. They're trying to balance the pH. But it is a razor-thin tightrope. If you inject too much ammonia, or if it concentrates in specific pockets of the system, you solve your general corrosion problem, but instantly introduce the exact chemical environment required for ammonia stress corrosion cracking.
It's unbelievable. You trade a visible, measurable thinning problem for an invisible, sudden cracking problem.
That's exactly what happens.
But from what I read in the API standard, the ammonia alone isn't always enough to trigger aggressive cracking. There is a massive environmental wildcard that hypercharges this reaction, right?
Yes, oxygen.
Oxygen. The documentation is incredibly clear that contamination with even microscopic trace amounts of air or oxygen dramatically increases the tendency toward cracking.
Oxygen is the catalyst that turns a latent vulnerability into a catastrophic failure, especially in anhydrous ammonia environments.
Okay, let's break down the chemistry of that. Anhydrous means completely water-free, pure ammonia. Why does a tiny trace of oxygen in a water-free environment cause the metal to self-destruct? Because, I mean, I thought oxygen was usually required to form protective oxide layers on steel.
That is true, but only in aqueous environments.
Meaning systems where liquid water is present.
Right. In a water-based system, oxygen helps form a stable, uniform, passive iron oxide film that protects the steel underneath. But in an anhydrous ammonia environment, the lack of water completely changes the electrochemistry.
Because without the water, that protective rust layer just can't properly form.
Exactly. You cannot form a stable passive film. So instead of protecting the steel, the trace oxygen acts as a potent cathodic depolarizer.
Cathodic depolarizer. What does that actually mean for the metal?
It creates highly localized, aggressive, microscopic galvanic cells right at the surface of the metal.
A galvanic cell, so it's basically creating a microscopic battery on the surface of the steel.
That's a really good way to visualize it. Because you don't have a uniform protective film, the oxygen facilitates an accelerated electrochemical reaction. It acts as the cathode, literally pulling electrons away from the weakest points in the steel's atomic lattice.
And where are the weakest points?
The high-energy, disordered grain boundaries in the heat-affected zone.
Unbelievable.
The oxygen essentially paints a microscopic electrochemical target on the grain boundaries, allowing the ammonia to rapidly dissolve those bonds. The anodic dissolution at the crack tip becomes highly hypercharged.
That is terrifying. It means you don't need a massive influx of air to cause a failure. A single faulty valve seal that lets in, just a whisper of atmospheric oxygen can initiate cracking across an entire unit.
It fundamentally changes how you have to operate the plant. You are no longer just managing pressure and temperature, you are managing the parts per million chemical purity of the process stream.
Wow. Okay, let's shift gears and talk about the actual physical assets. We know the metallurgy, we know the stress, we know the chemical trigger. Let's map this onto the refinery itself.
Good idea.
Where does this happen? The text maps the damage to very specific process units and equipment. We already talked about copper-zinc heat exchanger tubes. But the text identifies a very specific location within those exchangers as the most highly susceptible zone. It calls it the rolled area of the tubes. What is that?
The rolled area is the mechanical choke point of a heat exchanger. To understand the vulnerability, you really have to look at how a shell and tube heat exchanger is physically constructed.
Okay, set the scene for us.
You have a massive, thick, solid steel plate called a tube sheet. This plate has hundreds, sometimes thousands, of precision-drilled holes in it. You take your thin-walled copper alloy tube and you slide it into one of those holes.
But just sliding it in doesn't create a liquid-tight seal, obviously.
No, it doesn't. To prevent the shell side fluid from mixing with the tube side fluid, you must mechanically seal that tube to the tube sheet. And the most common method is rolling.
How does that work?
An expander tool is inserted into the end of the tube. This tool has heavy steel rollers that rotate and physically push outward, stretching the thin copper tube until it violently crushes against the inner wall of the tube sheet hole.
So you are plastically deforming the metal in place just to create a friction seal.
You are cold working it to its absolute mechanical limit. The metal is permanently crushed and stretched. This rolling process leaves behind an area of extreme, localized residual tensile stress exactly at the transition point where the tube exits the tube sheet.
Man. So you have a susceptible copper alloy, and you have artificially injected a massive amount of residual stress via the rolling process.
Right.
And if the cooling water or the process fluid happens to contain ammonia, it's just a matter of time.
The triad is complete. The transgranular or intergranular cracks will almost always initiate right at that high-stress rolled transition.
Okay, now let's look at carbon steel equipment, because the footprint here is massive. We are talking about storage tanks, both atmospheric and pressurized, as well as vessels and piping systems that handle anhydrous ammonia.
It's a huge scope of equipment.
Right. So if I am a facility engineer, right, looking out over a unit, I see massive spheres holding high-pressure ammonia, and I see standard flat-bottomed atmospheric tanks holding low-pressure liquid ammonia.
Sure.
Does this mechanism care about the internal operating pressure? Like, does the high-pressure sphere crack faster than the atmospheric tank?
That is a common misconception, actually, and it's vital to correct it. The cracking mechanism fundamentally relies on total tensile stress.
Okay.
Now, operating pressure, which creates what we call hoop stress in the vessel wall, that certainly adds to that total stress load.
But it's not the primary driver.
It pales in comparison to the residual stress. As we discussed earlier, the residual stress is locked into a non-stress relieved weld, and its heat-affected zone are usually so extraordinarily high that they sit right at the yield point of the material, regardless of what the internal pressure gauge says.
Wow. So the weld is already holding on to maximum tension even if the tank is completely empty.
Exactly. The stored mechanical energy in the weld is the dominant mechanical driver here. Therefore, a massive atmospheric storage tank operating at essentially zero internal pressure is at severe risk of catastrophic failure if its welds were not properly stress relieved during construction.
That is wild.
Yeah, the chemical environment and anhydrous ammonia with a trace of oxygen will exploit the residual weld stress in an atmospheric tank just as aggressively as it will in a high-pressure sphere.
That is a very sobering reality for tank farm operators. You can't just rely on low operating pressure to keep you safe.
No, you definitely cannot.
Which brings us to the practical reality of fieldwork, inspection and damage detection. How do inspectors actually find these microscopic, hidden cracks before a million-gallon tank unzips or a heat exchanger catastrophically fails?
Well, the inspection protocols are precisely dictated by the material because, as we established, the cracking morphology and location differ between copper alloys and carbon steel.
Okay, let's start with copper alloys.
For copper alloys, the first line of defense isn't actually looking at the metal itself. It's looking at the chemistry.
You mean operational monitoring, like checking the pH and ammonia content of water draw samples.
Exactly. It functions almost like running blood work on the heat exchanger. You are constantly analyzing the cooling water or the process fluid.
Okay, let's unpack that. If an operator gets a lab result back showing a sudden spike in the ammonia concentration in a water draw, does that mean the tubes are already cracking?
Not necessarily. Water draw sampling is what we call a leading indicator. Tracking the pH in the ammonia parts per million helps you predict susceptibility before physical cracking initiates.
Ah, okay.
If you see an ammonia spike, you know the chemical driver of the triad has suddenly arrived. It gives you a window for preemptive intervention. You can adjust the process, blow down the water system to flush the contaminant out, or immediately schedule a physical inspection before the metal has time to fail.
And when they do deploy non-destructive examination NDE to physically check the tubes, what are the tools? The API protocols specify visual testing, or VT, to spot distinct bluish corrosion products on the copper, right?
Yes. The interaction between the copper alloy and the ammonia often leaves behind complex cuprammonium ions, which present as a very visible, unnatural bluish scale on the surface.
So if an inspector sees that blue tint near a tube sheet, they know ammonia attack is happening.
Right. It's a huge red flag.
But the visual cue isn't the crack itself. To find the actual cracks in those highly stressed rolled areas we talked about, the protocol mandates penetrant testing, or PT.
Penetrant testing is arguably the most effective tool for finding surface-breaking flaws in non-magnetic materials like copper alloys. The physics of PT are just perfectly suited for Ammonia SCC.
Because it relies on capillary action.
Right. Exactly. You meticulously clean the inner surface of the rolled tube. Then you spray a brightly colored, highly fluid liquid dye onto the metal. Because Ammonia SCC creates tight surface-breaking networks, capillary action forcefully draws that liquid dye deep down into the microscopic cracks.
It pulls the liquid in like a sponge.
Yes, exactly like a sponge.
Yeah.
Then you wipe away all the excess dye from the surface, leaving the metal looking clean again.
Okay.
Then you spray on a fine white powder called a developer. The developer acts like a blotter. It reverses the capillary action and aggressively pulls the trapped dye back out of the microscopic cracks, staining the white powder.
Wow. So the invisible crack suddenly appears as a stark, bright line indicating exactly where the rolled joint is failing.
That's right. It makes the invisible visible.
That works brilliantly for the ends of the tube that you can physically reach at the tube sheet. But a heat exchanger tube might be 20 or 30 feet long.
Very true.
How do you inspect the middle of the tube for cracks? I mean, you can't spray dye down a 30-foot pipe and actually see it.
No, you can't. For the vast length of the tube bundles, you must deploy eddy current testing, or ECT. This moves away from surface chemistry and relies entirely on electromagnetic physics.
Electromagnetic physics. How does an electromagnet find a microscopic crack?
An ECT probe is physically pushed down the entire length of the tube. The probe generates an alternating magnetic field. When this magnetic field interacts with the conductive copper alloy wall, it induces small, circulating currents of electricity within the metal itself. These are the eddy currents.
And those currents just flow smoothly as long as the metal is solid.
Precisely. The ECT machine monitors the electrical impedance of those currents. If the probe passes over a crack, even a transgranular crack that hasn't fully broken the inner surface yet, that physical void disrupts the flow of the eddy currents.
Ah.
The machine reads that disruption as a spike on the screen. It allows an inspector to rapidly scan hundreds of tubes and identify volumetric flaws or hidden SCC without ever needing visual access to the crack.
That is incredible technology. Okay, now for carbon steel, we are dealing with a magnetic material, and we are looking at massive welds on tanks and piping, not tiny tubes. What is the NDE approach there?
Well, for carbon steel, the focus is entirely on interrogating the non-stress-relieved welds and their associated heat-affected zones. Because the steel is magnetic, inspectors utilize techniques like wet fluorescent magnetic particle testing, or WFMT, for surface cracks.
And what about cracks that are deeper in?
Right, for probing deep into the volume of a thick weld to find subsurface intergranular cracking, advanced ultrasonic methods like shear wave or phased array ultrasonic testing are deployed. They basically bounce high-frequency sound waves through the steel and look for the ultrasonic reflections that bounce back off the crack faces.
So the inspection technology is robust, but ultimately, an inspector finding a crack means the engineering has already failed.
Oh, absolutely.
The goal isn't to find the crack. The goal is to prevent it from ever initiating in the first place. Which brings us to the mitigation strategies. We have to break the triad.
Yes. Break one leg of the triad and the mechanism stops.
We talked about how high-strength steel is dangerous, but for carbon steels with a tensile strength not greater than 70 kSi, there is an absolute mitigation: post-weld heat treatment.
Post-weld heat treatment, or PWHT, is the ultimate engineering countermeasure for carbon steel in ammonia service. We spent a lot of time discussing how the rapid cooling of a weld locks massive residual tensile stress into the atomic lattice of the HAZ.
Right.
PWHT is the process of safely erasing that stress.
I understand the goal, but physically what is happening? You welded the metal, it got hot, it cooled down, and now it's stressed. How does heating it up a second time fix the problem?
It is all about controlled thermal energy and atomic mobility.
Hmm.
When you perform PWHT, you don't melt the metal. You wrap the welded pipe joint in heavy ceramic heating pads, or if it's a small vessel, you put the entire thing inside a massive furnace.
Okay.
You slowly bring the temperature of the steel up to a very specific critical range, typically around 1100 to 1200 degrees Fahrenheit for carbon steel.
Which is very hot, but well below the melting point.
Yes. You hold the metal at that temperature for calculated soak time, usually an hour per inch of metal thickness. At 1200 degrees, the atomic lattice of the steel becomes slightly plastic. It isn't liquid, but the iron atoms vibrate with intense thermal energy.
It's like giving the atoms a warm bath.
That's a perfect analogy.
Yeah.
The atoms have enough mobility to slide past each other microscopically. The severe microscopic traffic jams, the distorted crystal structures, and the immense tension created by the rapid cooling of the weld, they're all allowed to slowly untangle.
Wow.
The locked-in residual stress safely dissipates into heat and microscopic plastic flow.
So the metal essentially relaxes.
It completely relaxes. Once the soak time is complete, you cool the metal down very slowly and evenly. When it returns to ambient temperature, the physical weld is still there, but the invisible residual stress is gone.
And without that stress, the cracking triad is broken.
Completely broken. Even if the anhydrous ammonia and trace oxygen are introduced to the pipe, the chemical environment has no stored mechanical energy to exploit. The grain boundaries are no longer under tension, so the ammonia cannot tear them apart. The mechanism is neutralized.
That covers the mechanical mitigation beautifully. But what about the environmental mitigation? The API standard notes the other major preventative measure is absolute environmental control, preventing contamination with even small amounts of air or oxygen.
Right.
We said trace oxygen acts as the catalyst, hypercharging the galvanic attack. But think about the logistics of this. We are talking about massive atmospheric storage tanks holding millions of gallons of liquid ammonia. How on earth do operators keep an asset that large perfectly, entirely oxygen-free?
It's easily one of the most rigorous operational challenges in a chemical facility. You cannot simply empty an ammonia tank for inspection, open a hatch to the atmosphere, and then fill it back up. The moment atmospheric air fills that void, you have contaminated the system.
So how do you manage the vapor space?
You utilize strict inner gas blanketing. Operators continuously pump high-purity nitrogen gas into the vapor space of the tank. The nitrogen acts as an inert physical barrier.
Okay, so it displaces the air.
But it ensures that any volume inside the tank not occupied by liquid ammonia is occupied entirely by nitrogen, not atmospheric air. Nitrogen will not catalyze the electrochemical reaction the way oxygen does.
So what about when a system is completely shut down and open for maintenance? I mean, the air definitely gets in then. How do you restart safely?
The startup and shutdown procedures are incredibly complex and strictly enforced. Before anhydrous ammonia is ever reintroduced into a newly built piping system or a tank that has been open for inspection, the entire system must be painstakingly purged.
You physically push the oxygen out.
Yes. Operators will use continuous sweeps of steam or nitrogen to completely evacuate the atmospheric air, and they monitor the vet points with highly sensitive oxygen analyzers. They do not introduce a single drop of liquid ammonia until the analyzers read effectively 0% oxygen.
So the margin for error is non-existent.
It is razor thin. If a vacuum breaker valve malfunctions during operation or a pump seal fails and pulls a tiny vacuum, allowing a whisper of atmospheric air into the process stream, The inert blanket is compromised.
And then what?
The galvanic cells form at the microscopic level, the anodic dissolution accelerates at the grain boundaries, and the clock on ammonia stress corrosion cracking starts ticking immediately.
It is a phenomenal intersection of disciplines. I mean, you have operators managing parts per million oxygen limits on massive tanks, inspectors using electromagnetic fields to find microscopic disruptions in copper lattices, and materials engineers dictating the exact tensile strength limits and heat treatment temperatures of the steel.
It proves that you cannot manage fixed equipment integrity in a silo. The mechanical physics dictate the chemical vulnerability, the chemistry dictates the required inspection technologies, and the inspection limits dictate the engineering mitigations. Every variable is locked together.
Absolutely. I want you, the listener, to walk away with a specific thought to mull over. Consider the concept of the silent, invisible memory of metal.
I love that concept.
Yeah, think about it. A massive carbon steel vessel can sit peacefully in a tank farm for 30 years. To the naked eye, it is completely inert, doing exactly what it was designed to do. But secretly, locked deep within the atomic lattice of its heat-affected zones, it is harboring the violent residual stress of the exact day it was welded 3 decades ago.
It never goes away on its own.
The metal never forgets that stress. It only takes one slight deviation in process chemistry, a little too much injected ammonia, a whisper of oxygen slipping past a degraded seal for the environment to give that steel the excuse it needs to finally remember that stress, and silently, catastrophically tear itself apart from the inside out. That wraps up our technical deep dive on this mechanism. Don't leave your exam or your asset integrity to chance. Head over to magintegrity.ca right now to subscribe to our full premium library, download the Visual Slide Companion Pack, and master API 571. Until next time, keep your assets safe and your inspections rigorous.